it's time to cut some corners and tie a bunch of things together. And what we're going to do is apply this idea of net dipoles so that we can find the intermolecular forces to our structures that we've drawn in 3 dimensions previously. And I'm going to break things down to 2 imaginary categories. And those 2 imaginary categories are nonpolar, if all attached atoms are the same, and always polar. So we've got 2 categories here, and I'm just going to declare that one is P, and that's always polar. And then we'll have N with a little star or an asterisk by it, and that's going to be nonpolar if all attached atoms are the same. With the fine print of otherwise polar. Okay, so this is going to be nonpolar unless it has different atoms attached, and then this one for P is going to be polar. And that's going to be the deciding factor in running through this flowchart right here. Conveniently, this is all already labeled on this setup that I gave you, but we're going to pretend that we don't know that, and we're going to go back and brute force it by hand. I'm going to look at maybe sketch in with pencil the individual dipoles, and then we can come up with what we expect to see for a net dipole. At least I would if I had any idea where my pencil was. There it is. In a situation like this, you've got 2 atoms. They're going to share equally if they're both the same, and they're not going to share equally if they're not both the same. So without question, in a situation like this, it's going to have to end up, I'll just label it, N star, all right? Nonpolar, as long as all the attached atoms are the same. And that doesn't come up on the sheet because that's only 2 atoms. When you get to here, you see this situation like we did with CO2, where you have 2 attached atoms and a central atom, and as long as that atom are equal in strength, they have the same electronegativity, they're going to cancel out. But we saw that if they were different atoms, then those individual dipoles might not cancel out, and it might end up polar. And what I'm saying there is, it would be nonpolar if the attached atoms are the same, but it's going to be polar if they're not. So this situation here with linear, so if we had individual dipoles going in either direction there or either direction there, they would cancel out as long as these 2 atoms are the same. So we're going to label that one as nonpolar, if, right? Nonpolar if all attached atoms are the same. When you look at trigonal planar, we did an example just like that with BH3. It comes out nonpolar because all those individual dipoles equal in length at equal directions cancel out. But if any of those atoms are different, like we saw with this BH2F, then we end up with a net dipole. So this one ends up nonpolar. I guess we should put our little star there. When you look at this, take a look at the symmetry. We have good symmetry left to right, but we have no symmetry there or no symmetry there, as opposed to this one where we have symmetry, symmetry, symmetry. So we're going to start looking for symmetry, and in this case, whether this dipole is up or down, whether this dipole is up or down, there's nothing here to cancel it out. This is always going to be polar. And your dipole on that is going to be right up and down the middle, towards the higher electronegativity. So this blue line I drew, that's where you're going to expect to see your net dipole. Moving right along, you see a situation where we've got very good symmetry in multiple directions. This one will end up nonpolar, as long as all attached atoms are the same. And just like the previous one, this is a nonpolar structure with something missing. It's got a non-bonding pair there. We have either up or down on these, and there's no way that they can cancel out. It's that triple high 5 scenario. There's no way that they can cancel out. So you are going to end up with a net dipole up and down. That's not the greatest arrow. Depending on where the higher electronegativity is. Looking at this, just like we saw for the bent structure, let me just write this here, polar, and this one's always going to be polar as well. Just like the trigonal planar based bent, these 2 things can't cancel out vectors, and so you're going to end up with a polar structure always. For our trigonal bipyramidal, again, we've got all this great symmetry. This one's going to be nonpolar if all the attached atoms are the same. And just like we saw with the trigonal planar-based bent right here, you're going to have a dipole right here, and I'll draw it in, right here, because there's nothing to cancel it. And again, that arrow will point in the direction of wherever your higher electronegativity is. This and this will cancel out. And that it's like a footnote maybe, but if this and this had the same electronegativity, and this and this and this had the same electronegativity, but they didn't match, you'd probably still consider that nonpolar. Looking at this, again, you have a situation where there is no way to cancel out this component, so this one's going to have to be polar, either towards that atom or towards the central atom. There's no way around it. And then this one could be nonpolar if all the attached atoms are the same. That's, again, one of our linear situations. Octahedral. Look at all that symmetry. That has to be a situation where it can be nonpolar as long as all those attached atoms are the same. And again, there could be like some foolishness where those are the same as each other, those are something else, and those are something else. But just think of it as all the attached atoms being the same. And if this and this are going to cancel out or balance out, and we have one here and not here, that means that that one has to be polar. There's no way for this not to be polar, and so we are going to end up with polar there. This one here, cancel and cancel, so it will be nonpolar as long as all the attached atoms are the same. And for the same reason that our T-shaped trigonal bipyramidal structure ends up polar, this is going to end up polar. And then we've got a linear one, which could be nonpolar if all the attached atoms are the same. And then I don't know if I left the other one in, but if you had pentagonal bipyramidal, everything attached the same, nonpolar. If not, polar. So what we're looking for, symmetry and uniformity in the composition. And again, I've summarized all those here, but I kind of wanted to visually show as you're planning ahead for how you're going to label your own three-dimensional drawings.